Hi everyone, let's have the last part of lecture 2, part 3 of Introduction to Descriptive Analytics. After obtaining the average of the sample data, the sample mean X bar, and the sample standard deviation S, you can obtain a confidence interval for the mean of the population. So here you can build a confidence interval by obtaining a significance level alpha. So using t-distribution, you can actually build a confidence interval for the mean of the population. And also you can do the same for the sigma. So when you calculate S as the sample standard deviation, you can build a confidence interval with alpha and using chi-square distribution for the standard deviation of the population. Okay. So let's see how the mean and standard deviation are related to each other. So here we had two concepts, Chebyshev's theorem and empirical rule. By Chebyshev's theorem, regardless of the shape of the distribution, so it doesn't matter if this distribution is symmetrical or it's skewed, we can apply the Chebyshev's theorem. So this theorem says at least 75% of all observations will fall within plus minus 2 standard deviation of the mean, and 89% of all observations will fall within plus minus 3 standard deviation of the mean, and at the end 94% within the 4 standard deviation of the mean. So let's show this in a graph here. Let's say this is our distribution. So here I'm assuming a symmetrical, but it doesn't need to be symmetrical. Okay. So here, let's say is our mean. Okay. So the plus minus 2 standard deviation, that means here mu minus 2 sigma and here mu plus 2 sigma. So this Chebyshev's theorem says that 75% of the data observations will fall within this range. So here it would be 75%. Okay, and for 3 sigma, here let's say is mu minus 3 sigma, and here is mu plus 3 sigma. So this range, I mean the probability would be 89%. Okay, 89%. And for 4 sigma, here, for example, mu minus 4 sigma, and here mu plus 4 sigma, the percentage of the observations within this range would be 94%. Okay, so one more time, we can apply the Chebyshev's theorem for any distribution. It doesn't matter if it's symmetrical or skewed. Regardless of the shape of the distribution, we can apply the Chebyshev's theorem. Okay. So here we have the general definition of the Chebyshev's theorem with k standard deviation of the mean at least 1 minus 1 over k square percent of the values are here. So here k equals x minus x bar over s, or x minus mu over sigma. Okay, so as you see here, the Chebyshev's theorem would be valid for any k greater than 1. Okay, so it's not valid for k equals 1, but for any value greater than 1 for any shape of distribution, we can apply the Chebyshev's theorem. Okay. Besides the Chebyshev's theorem, we have another concept here which is called empirical rule, and this rule just only applies on symmetrical or bell-shaped distributions like normal. So we cannot apply empirical rule for um, non-symmetrical distributions. Okay, we just can apply this for symmetrical or bell-shaped distribution like normal. So by this rule, 68% of the observation will lie between one standard deviation of the mean. I mean, mu plus minus 1 sigma. Okay, and 95% of observations will fall between 2 sigma of the mu, so mu plus minus 2 sigma, and 99.73%, almost all observations, we can say approximately, will fall within the range of 3 sigma from mu, okay, mu plus minus 3 sigma. So this is the empirical rule and can be applied only on symmetrical or bell-shaped distributions like normal, okay. Okay, let's here show graphically the empirical rule. So let's assume that we have a symmetrical distribution like normal here, and here is the mu. So the 1 sigma would be somewhere, let's say around here. Okay, so mu minus sigma, mu plus sigma. Okay, so this range will include 68% of the data, 68%. Okay, and if we consider 2 sigma, so let's say here would be mu minus 2 sigma, and here mu plus 2 sigma. Okay, so this range will include 95% of the observations of the data. And if we go for 3 sigma, like here mu minus 3 sigma, and here mu plus 3 sigma, so we can see almost all observations would lie within this range. So this is approximately 99.7%. Okay, so this is the empirical rule for symmetrical distributions. Okay, so here, in order to show how far a particular x is from mean, we can use the z-score relation, z-score formula. So z-score would be x minus mu over sigma. Okay, so for example, let's assume that the mean of a population is 50 and the standard deviation is 10. So if we consider a value like 65, then we can say 65 minus 50 over 10 becomes 1.5. So that means 65 is at 1.5 standard deviation of the mean. Okay, and we can also use a z-score formula to obtain the outliers. For example, we can say any observation beyond plus minus 3 standard deviation of the mean can be considered as outliers. So here we can say, so here we can obtain the range by z of 3. So that would be mu minus 3 sigma and mu plus 3 sigma. So here we have a range. So here is the mu. So here is the mu minus 3 sigma and mu plus 3 sigma. So any observation beyond this range would be considered as outliers. Okay. In this slide, the functions in Excel for calculating mean, median, and so on. I mean, all the measures that we had so far, the mode, percentile, quartile, IQR, min, max, range, standard deviation, covariance, and coefficient of correlation. Yeah, you can use these functions in Excel for any data set to obtain these measures. Okay, so during the live session, also in another recording, I will introduce the functions in R as well, by having an example and a sample data set. You'll see how can we implement these measures in R as well. Okay. So here we have an example activity. So I will provide a recording for this as an example for one variable, and then for the rest, we will practice this during the live session. Okay, thank you.